Today I'll upload it. I'll upload the slides today. So generally, what will happen? What will they give you? I think this is something I told you guys already. This is something you should have done in electrical sciences, but I'm just quickly revising it because so that see understand this. This is just a revision. We will do far more advanced circuits in this course, and what you have to learn, it's just to bring you up to basics, and after that you should be able to analyze circuits in a much more intuitive way. Okay, but I'll just first take you through the initial steps that you should have done in electrical sciences. Okay, but because since you have done electrical sciences almost 6-7 months ago, I'm just quickly revising it. So for example, let's say the general procedure for finding DC and AC analysis, let's say you are given a circuit like this. So this is the bipolar junction transistor circuit given to you. Okay, so before I start discussing about amplifiers, so in this circuit you are not even supposed to find voltage gain or anything. You are just required to find the DC operating current. So whenever you are given a circuit like this, the first step, I teach this in electrical sciences, the first step is to find the DC operating point. Whenever you are finding DC operating point, what should you do? You should open circuit the capacitors, and if there are any inductors, you should short circuit the inductors. But there are no inductors in the circuit, so just open circuit these capacitors. So once you open circuit these capacitors, you are left with this resistor doesn't come into picture anymore, because if you open circuit this capacitor, you are going to have a resistor. You are going to have a resistor RE here, and that resistance, I think this is RL here, this is RL. That resistance is anyways carrying no current, so the DC voltage across that will be 0. So that resistor won't come into the picture. Okay, so now open circuit this capacitor, you will be left with a circuit like this. And this circuit, I told you guys in the last class how to solve this. Replace this part, this branch, the voltage divider network by its Thevenin equivalent. Okay, once you replace it by a Thevenin equivalent, then you can solve. You should write 2 KVLs, Kirchhoff's voltage law, in 2 loops, and you can get the answer. So what is the goal of doing DC operating point? The reasoning we said that was, we said for a BJT to act as an amplifier, you have to keep the BJT in this region. So in this region where your collector current is independent of the collector to emitter voltage. So in fact, when we will be very soon giving you guys the first, I think very soon, probably in the second week of February, you may not get to access the software, but if you are interested, you can. There are a lot of open softwares called LT-Spice. You can play around with the softwares. There will be a lot of instructions on YouTube and everywhere how to use those softwares. Okay, so we have some issues for giving you permission for direct access in the labs. So that's why we will not be able to give you direct access this semester. So you may have to use some online softwares. There are a lot of free softwares available. One of them being LT-Spice. Okay, so LT-Spice is a software. So wherein the usage of the software, it's all there, and you can find lots of YouTube videos how to use the software and all of that. Okay, you can, if you are interested, you can refer to that. But we will show you, at least we'll ask, the TAs will demonstrate to you how to run the simulations. Yeah, the labs will be, as of now, the tentative plan is that the teaching assistants will come and explain you guys how to run a simulation. We'll have some 20 students per lab session. A teaching assistant will come and through a Google Meet session, they'll open a Cadence window and show you how to run simulations. So that you just get a feel for, so whatever we teach in the class, we'll try to give a similar question in the lab. So they will simulate in the lab and show it to you. Okay, so that is the tentative plan decided by the IC. So that's the plan we have right now. Okay, so we'll see how it goes. Initially the plan was to give access to you guys, but it seems like there was a problem with that. There is a problem with that. Yeah, timings will be between 6 to 10, so that they will decide. They will mail you guys soon. That decision will be made to you. Okay, so yeah, so what we do is, for example, if you want to plot this characteristics on a software, or you can actually take a discrete bipolar junction transistor. What I showed you guys, the 3-legged device. It looks like a 3-legged device. You take the discrete bipolar junction transistor and apply a DC voltage source like this between collector and emitter, and a base and emitter, and keep varying both those voltages. and you can actually generate a plot like this. Probably your first assignment, we will show this for MOSFETs. Okay, so that's what you will be more interested in. We will try to show this plot for a MOS circuit in your first assignment, lab assignment. Okay, so I'll come back to the lecture now. So what we are discussing right now is that we said if you want to have amplification, keep your transistor in this region. So this act of keeping the transistor in this region, it's called biasing. Okay, so we call it biasing. And if you have to bias it in such a way so that it remains in active region. So it has to look at this. In this region, it has to have a finite collector current. It cannot have zero current. Then there is no amplification. You need the device to have a finite collector current and a finite collector base emitter voltage and a base collector to emitter voltage. So this point ICQ comma VCQ and for a corresponding VBEQ. Okay, so this is called as a quiescent operating point. And in the last two lectures, we were discussing about this, and in the last lecture, we solved some problems on how to find the quiescent operating point given a circuit to you. Okay, that's what we found in the last class. What happens in reality? This is DC biasing. After that, what do? You apply an AC signal in series with this. So, for example, okay, so I have actually taken an example, but anyways, I can show it here as a figure here. You can apply a small signal in series with your DC voltage source. And then if you feed it to a base of a transistor, a small change in the voltage will result in a good change in the bias current. When that bias current flows through a resistor, the small signal current DI flows through the resistor, it's going to generate a sinusoidal output. See, what are you doing? There is a DC voltage VBB. So you have a DC voltage VBB. On top of it, you are applying a small sine wave. This is the small signal you wish to amplify. This, when you feed it to a BJT, what will it do? There is a DC VBE, there is a DC VBE quiescent, plus there will also be a small VBE, which is the small signal voltage. In response to that, a current GM times VBE will be generated in the BJT device. That current, when it flows through this resistor, it's going to have a sinusoidal variation. Because the current is sinusoid, VB is sinusoid, so the current will also be sinusoid, the voltage will also be a sinusoid. So if you apply a small voltage here, you can expect a large voltage at the output. Now the previous question was just to show you how to find the DC operating point, that's it. I just gave you, remove the capacitors. Now you have a circuit like this. This circuit I solved it in the last class. This circuit, this one, I solved it in the last class. How to solve it, I solved it in the last class. Okay, this circuit, I already solved it in the last class, so I don't have to repeat it. That's why you have to write one KVL in this loop and one KVL in this loop and you will get the answer. Yeah. Okay, so I'll just come back to tutorial 1. So this is your tutorial 1. Before going there, I thought I'll just quickly discuss some one or two questions in tutorial 1. So this is the circuit given to you. So if you're asked to find, what you're asked to find is the parameters R pi, GM and R naught in the circuit. You're supposed to find these 3 parameters for the circuit given. I told you guys all those 3 parameters are uniquely determined by the quiescent collector current. Okay, they're all uniquely determined by the quiescent collector current. It is given to you, beta is given to you, beta is 100. And what else is given to you? The early voltage VA is given to be 50 volts. All these parameters are now given to you. You are supposed to find the small signal parameters R pi, GM and R naught. Okay. So how do you find this? So first step, open circuit the capacitor. You will be left with, if you open circuit the capacitor, you will be left with whenever you are finding the DC quiescent operating point, you remove the capacitor, open circuit it, you will be left with a circuit like this. So you have a 100 kilo ohm resistor and a current of 1.01 milliampere. Now what is this current? So this current here is it the collector current? 1.01 milliampere, is it the collector current? See, apply KCL at this node. Apply KCL at this node. If you apply KCL at this node, what will you get? You will get this current here is collector current. The current flowing through this is the same as the current flowing through the base terminal. So therefore the current that's flowing through this device here, it is actually base current plus the collector current, which is nothing but the emitter current. So 1.01 milliampere is your emitter current. Okay, so 1.01 milliampere, this is your emitter current. Now once you know emitter current, can you find what is the base current? Yes, base current is what? IE by beta plus 1, because it is an active region. So we can directly say IE by beta plus 1. And what is your collector current? Your collector current will be beta by beta plus 1 into IE. Okay, so your IE is 1.01 milliampere into 100 by 101. So if you use it, you will get 1 milliampere as your quiescent collector current. The quiescent collector current in the circuit is 1 milliampere. Okay, so that's what I've written here. The quiescent collector current in the circuit is 1 milliampere. That's it. Once you find the collector current, you know everything you need to know about the circuit. You can find all the other parameters. What is your GM? GM is ICQ upon the thermal voltage, which happens to be 1 milliampere by 26 millivolts. You get this around 38.5 milliampere per volt. So if I use 1 milliampere of current, I can get a GM of 38.5 milliampere per volt. R pi will be beta upon GM. So it will be beta into 100 into VT upon ICQ. I discussed all these parameters in the last class itself. I told as soon as you are given a BJT circuit, the first thing you should look for is if you are asked to find the small signal gain, you have to first find the small signal parameters. To find the small signal parameters, the first thing you should do is compute the collector current, the quiescent collector current. So the quiescent collector current will be 100 into, once you find the quiescent collector current, all the small signal parameters can be immediately formed. They are uniquely identified by the collector current. You know GM, next is R pi. R pi is beta by GM. So or you can directly use the formula. So GM is IC by VT. So you will get 100 VT by ICQ, which is around 2.6 kilo ohms. Okay, R naught is VA upon ICQ. VA is 50 volts and 1 milliampere, so you get 50 kilo ohms. This is your R naught. What is the use of open circuiting? Now, whenever you are finding DC, what is DC? For any circuit, if you are finding DC operating point, capacitor, the DC current flowing through the capacitor is 0. Right? Is that okay with you? If you take a capacitor, the DC current flowing through the capacitor is 0. Because the DC current is 0, we will treat it like an open circuit. So this you must have, is that okay, or you guys, they must have told you in ES, right? You have to open circuit capacitors, find the DC operating points, or see, it's a very simple thing. A capacitor will not have any DC current flowing across it. Okay? If any DC current flows through the capacitor, then the voltage will keep ramping up. But that doesn't happen in reality. So what happens is, you can immediately see a capacitor offers what is the impedance of a capacitor, the frequency response impedance. Can I say it's 1 by j omega c? 1 by j omega c is the impedance of a capacitor. At omega equal to 0, that is your DC frequency, the impedance of a capacitance is infinity. This term becomes infinity. So which means it's open circuit. If some impedance is infinity, it's an open circuit. Whenever you are finding DC, you have to open circuit the capacitor. For AC small signal model, the capacitor will be a short circuit. Okay, that's how you find AC and DC models, AC and DC analysis. Okay, so next in the question itself, you are supposed to draw the small signal model. Okay, draw the small signal equivalent model. So if you are asked to draw, so this is the BJT, just replace your BJT by the small signal model. So whenever you are asked to draw the small signal model, what you should do is you should short circuit DC voltage source. The small signal model will be just, small signal model is only for BJT. If I ask you for the whole circuit, 100K should also be present. Okay, the GM R pi model is for the BJT. But for the amplifier, if I say amplifier, 100K is also part of the amplifier. So that should also be there. So this is your small signal model. So you replace the BJT, replace your BJT with its small signal model. So if you replace it, this is your collector, emitter, base. So what did I do? I replaced the BJT here. From the collector, I have a current of GMVBE or GMV and collector to emitter, there is a resistance R0. Okay, and here this is now base terminal. So this resistor is 100 kilo ohms. From base to emitter, there is a resistance of R pi and a capacitor at the input. So that's what I've drawn here. Find the small signal parameters, draw the small signal, replace the 3 terminals of the BJT by the 3 terminal small signal model. That's it. That gives you your small signal model. Okay. Now, in this circuit, is that question okay, guys? Well, I'll move to the next one. The second question, we haven't completely come to this part yet in the analysis. What we are going to teach you in the course, we haven't come to this part yet. But, yeah. Is that okay? What do you guys want from this? You want me to say something or you just want me to go to the slide? Yeah. Okay. So now the second circuit, you are given a circuit like this and we are asking you to find the equivalent resistance at this point. I've put an arrow here and I'm asking you to find the equivalent resistance at this point. Whenever you are given a circuit like this, first step, equivalent resistance in all of these quantities, they are AC quantities, small signal quantities. So in a small signal analysis, first step you should know to draw the AC equivalent circuit. Okay. So AC equivalent, whenever you are drawing AC equivalent circuit, short circuit DC sources, open circuit current sources. Okay. So first you should draw the DC equivalent and compute the operating point, which is ICQ. First, draw the DC equivalent, compute your collector current. Once you compute the collector current, you will know all the small signal parameters, R pi, GM, R0. You will know all the 3 parameters. So this completes your everything you need to know for the circuit. You know once you compute the collector current. Yeah, I'll repeat it. Okay. So I think I'll take one specific problem and then I will solve it so that it will become clear that way. Okay, here I'll show the step-by-step process. So for example, you are given a circuit like this. So whenever you are given a circuit like this, and then you are supposed to find the small signal gain for the circuit. So before you find small signal gain, you need to know small signal parameters. To find the small signal parameters, you need to know the DC operating point. Okay, so therefore you have to first step is to find the DC operating point. Okay, so first step you need to find the DC operating point. After finding the DC operating point, you will know the collector, the quiescent collector current. Once you know the quiescent collector current, you will know the small signal parameters. The small signal parameters are GM, R0, R pi. Once you know the small signal parameters, the next step you will do is do what we call AC equivalent. You will be drawing an AC equivalent of the circuit. In the AC equivalent, you will short circuit DC sources, DC voltage sources, and open circuit DC current sources. Voltage sources should be short, DC current sources should be open. Once you do that, then you perform the small signal analysis. Replace your BJT with a small signal model and perform this small signal analysis. That's the general steps involved. So first, look at the circuit. What I'm doing here, I'm first drawing the DC equivalent. The DC equivalent, how do I draw it? I'll remove capacitors. Capacitors will be open circuit. Everything else will remain the same. AC sources will not be present in DC analysis. So in DC analysis, I will short circuit AC sources. Voltage source will be short, means it will become a short circuit. I'll replace it by a short. If there was a current source, then I would have open circuited it. I'd remove the current source and analyze it. The node will be open. And capacitors will be open circuited. These capacitors will be open circuited. Once I open circuit the capacitor, I'll be left with only this much of the circuit. So that's what I've shown here. It's DC equivalent. Okay, so your capacitors are open circuit, small signal AC sources are shorted, and you draw a DC equivalent. The next step is AC equivalent. What do you do in AC equivalent? In AC equivalent, you will short circuit the capacitors. Short circuit the capacitors, short circuit the DC voltage source. Okay, DC voltage sources should be short. Whenever you are doing AC equivalent circuit, all the DC voltage sources should be short circuit. Even current sources should be open circuit. If there was a current source, remove the current source, open circuit it. Then draw the circuit. So this becomes AC equivalent. Now look at this. This I have represented it as ground. It means that it's not actual ground. It's called as AC ground. It's called as an AC ground or small signal ground. Okay, it's not a real ground. I mean, it's not a ground where see, when I say a real ground, the potential doesn't change. Even see, DC voltage depends on VCC. But for AC signals, this node will not have any variations at all. So as far as small signal is concerned, this node will be at small signal ground. Small signal, it will be at AC ground. So that will be at ground. This is anyways at ground, so that node will be represented as a ground. And I've shorted this capacitor here. This capacitor is also short circuit. Once you draw the AC equivalent, replace the BJT with the small signal model. So take your BJT circuit here. That's what I've done here. See this resistance RC now. I can repeat AC ground. Okay. So let me ask, put a question like this. So let's say I have a resistor like this, another resistor like this, and I have connected a 1 volt DC source. Okay, this resistor, let's assume, is 1 kilo ohm, 1 kilo ohm, and let's assume I'm applying, this is the ground here, a 1 millivolt AC signal. If I'm applying a 1 millivolt AC signal, if I ask you, let's assume this node voltage is Vx. What is the node voltage Vx? What is the node voltage Vx? Yeah. Is that okay with everyone? That node voltage Vx is independent of whatever I apply here. Okay. The AC voltage source is 1 volt, but the DC voltage, that because of the voltage of a DC source, it is independent of whatever I apply. It will always be staying at Vx. So now, whenever you are given a circuit which contains both AC sources and DC sources, we apply the principle of superposition and analyze the circuit. In the principle of superposition, you retain one guy, make the other guy 0. So you retain AC and make DC 0 in AC analysis. In DC analysis, you retain DC and make AC 0 in the DC analysis. Okay. So what I'm doing here, so this node voltage, if you see, as far as AC signal, this node Vx doesn't contain any alternate or variations at all. Even though I'm applying a 1 millivolt sine wave, there will be no variation, no sinusoidal component present at the node Vx. So that node Vx has no variation. So as far as a DC circuit, as far as the AC circuit is concerned, if I make the DC voltage source 0 here, it will be shorted to the ground. So therefore, this node, even though there is a DC voltage source, since there is no variation, once I short it, replace with a short circuit, it will usually short to the ground. We call it as AC ground. Okay, yeah. Okay, so this is called as an AC ground, and this is anyways, it's ground both for DC and AC. Okay, so that's the small signal AC equivalent. Once you draw the AC equivalent, replace the BJT with the small signal model. So now look at this. I have written RC parallel RL. That's because This is your one node RL, the other node of RL is at ground, the other node of RC is also at ground. So therefore RL and RC will be in parallel. The two nodes are same for the devices, right? If you have two resistors or two devices with two nodes being common, then or the voltage across them is same, then the two devices will be in parallel. So this becomes RC parallel RL. Okay. So now this is your replace your BJT with this device and you have your small signal model. That's it. Now you have to perform KCLs and KVLs and derive the voltage gain expressions. Okay, that's it. That's the small signal model. This is how you have to perform the analysis. Now let's go back to a tutorial question. You are given a question like this. You are supposed to find the equivalent resistance. Usually when we ask you to find equivalent resistance, it always implies incremental resistance because these are nonlinear devices. When they are nonlinear devices, you cannot find resistance generally. You have to find only incremental resistances. You can only find incremental resistances. Okay, so or small signal resistance. So now we know, okay, we are supposed to find incremental resistance. If you are supposed to find incremental resistance, you need to know the small signal parameters for the circuit. And remember, all the small signal parameters depend only on the quiescent collector current. So if your operating point changes, if your quiescent collector current changes, then all small signal parameters will also change. Okay, so that's something you have to keep in mind. And that's why I call it as an incremental model. That small signal parameters or model is valid only for a certain collector current. If you change the collector current, then you have to recompute all the parameters. So this circuit, they have asked you to find the small signal equivalent resistance seen at this node. So usually we will give you one node. So if I'm pointing at this node, it usually means this node with respect to an AC ground, with this node with respect to a ground. So we are supposed to find the resistance between this node and ground. So how do we find it? First step, your goal is, because it's a small signal resistance or incremental resistance, your goal should be to first find out the small signal parameters. To find the small signal parameters, you need to know the quiescent collector current. Now, first we'll do a DC analysis. If I'm going to do DC analysis, there is no AC source in the system, so I can keep the circuit as it is. Now look at this. This is 1.01 milliampere is the current that is entering here. That is getting split as two currents. This is your quiescent base current. This is your quiescent collector current. Right? This is your quiescent base current. It is splitting as two currents. So 1.01 will be milliampere will be equal to the quiescent base current plus quiescent collector current, or this is nothing but the quiescent emitter current. So that will be 1.01. So what is your quiescent collector current? Beta is given as, okay, see here you have to do a little intelligent calculation. Okay, in the first question here we have given you one thing. We have given you beta equals infinity and VA equals infinity. This is an interesting result. What happens if beta is infinity? What will be your base current? Your base current will be 0. That's it. You got it right? If beta is infinity, your base current will be 0. Is that okay? IC will be equal to IE. So if IC will be equal to your quiescent current will be equal to this. So therefore your IC will be 1.01 milliamperes. So then you can calculate R by R naught and R naught. What will be the value of, okay, let me give you this. What will be the value of R naught? Is that okay? It's infinity, right? What is R naught? R naught is VA upon ICQ. ICQ is 1.01, but VA is infinity. So R naught will also be infinity. It's open. Yeah. R naught will be infinity. So first step, in the first example, we will find out the equivalent resistance. So what are we going to do? R naught is infinity and your GM will be, you will find the equivalent GM and R pi can be found as well. Okay, GM and R pi can be found. GM and R pi can be found from the formula. So GM will be ICQ upon VT. And I think this is, if see, we generally, if you don't give a temperature, assume room temperature, 300 Kelvin. You can assume that. And R pi will be beta VT upon ICQ. So compute R pi, compute GM, you have your small signal model ready. Okay. So the first case, the small signal model, what will be the small signal model? So base, collector, emitter. So between base and emitter, you have a resistance R pi, and you have an impedance GM V pi, current flowing from collector to emitter. R naught is infinity further. This is emitter, emitter is at ground. Emitter is at AC ground, or that will be DC ground, it's same as AC ground as well. This is ground. R naught is infinity. And what are we doing here? In the circuit, I am shorting base to collector. It's a short circuit. So I have to short circuit these two nodes. Okay. Now look at this circuit. What can I represent GM as? This part. What is the voltage across? If I give you something like this, if I give you a circuit like this, isn't R pi infinity? No, R pi is not infinity. Yeah, sorry, you're right. I'm sorry. So you guys were just asking me, R pi is beta Vt by ICQ. R pi is also infinity. Yes, you're right. R pi is also infinity in the first model. Okay. So therefore, R pi I'll open circuit it. Okay. So I have a circuit like this. The node voltage across this is V pi. R pi is infinity. So let's assume you have a current source GM V pi, and the voltage across the current source is V pi. So if I increase V pi, what will happen to the current here? The current will also increase, right? If I increase V pi, current will also increase. So does this behave like a current source anymore? What is it behaving as? If I increase V pi, the current is also increasing. It's behaving like a resistor. Yes, it's behaving like a resistor. And what is the value of the resistance? See, the current, if I ask you, the current here is GM V pi. The voltage is V pi. So the resistance is voltage by current, it is 1 by GM. That's it. So what can you do? You draw the small signal model. I think I have derived a more general expression, but it's okay. In the first case, it will turn out to be 1 by G. Yeah, that's okay. The solution is fine. The first case, it will turn out to be 1 by GM. The equivalent resistance, if I ask you what is the equivalent resistance? Between collector to emitter, you can replace this GM V pi by a resistance of value 1 by GM. Okay, so now you are asked to find the equivalent resistance seen at this terminal. The whole BJT model is collapsed into a single resistor in this example. So the resistance will be, what will be R equivalent? R equivalent is nothing but the resistance seen from collector to emitter. So how do I find R equivalent? Apply a test voltage at this node. So I'm applying a test voltage Vx and measuring the current Ix flowing out of it. But I have only one resistor there. So I don't need to do analysis. I can directly say it is 1 by Gm. Okay? Is that okay with everyone? The equivalent resistance seen at this node is 1 by Gm. Yeah, is that okay, guys? If you have any doubts, you can ask me. Yeah. Now, in the next question. Here the base and emitter are the same. No. Base and emitter is not same. Base and emitter is not same. Emitter is ground. See, this is base terminal. Ideally, you had R pi between base and emitter. The emitter is at ground. And you had a current source of value GM V pi. This is your collector terminal. R naught is infinity. Okay, R naught, I'm not showing R naught because R naught is infinity. What are we doing? Base and collector are at the same voltage. I'm shorting base and collector. Okay, and this voltage is R pi, this V pi. This has always been V pi. Even with the resistor or without resistor, it has always been V pi. Now, because beta is infinity, R pi is also infinity. So we are left with circuit like that, a circuit that looks like this. Base and collector are short circuited. So there is only BJT now becomes a 2-terminal device. See, BJT is supposed to be a 3-terminal device, but now I have short circuited this. So now if you see, it only has 2 terminals. I have shorted base and collector. So therefore now it becomes a 2-terminal device. So we are telling you that in small signal, this 2-terminal device will approximate a resistor of value 1 by Gm. Okay, so now base is here. So now we are supposed to find the equivalent resistance at this node. That's what the circuit is asking you to do. I can see, anyways, this is the V pi. What did we do? We said, okay, if the current source voltage is Gm V pi, I can replace the resistance of value 1 by Gm. And the equivalent resistance is seen between collector to emitter. So that is simply 1 by Gm itself. That's it. Yeah. Okay. So fine. The next question is, with a finite beta. Beta is 100, Va is 50. If beta is 100, Va is 50, your collector current, what will be the value of your DC collector current? 1 milliampere. Right? You can solve that. Your DC collector current will be 1 milliampere. So then you can calculate all the three parameters. So now I will draw the small signal model. What will be the small signal model in that case? Between base and emitter, you have a resistance R pi. Between collector and emitter, there is a current of value Gm V pi. And there is an equivalent resistance of value R naught between collector and emitter. Okay, we have three resistors in parallel, and this voltage is V pi. Now again look at this. This current source, because I have shorted base and collector, what is the voltage across the current source? If I ask you what is the voltage, it is V pi. Now, whenever you have a voltage across the current, see, you can actually apply KCL and solve the problem as well. Okay, but I'll first, okay, let me do that. Let me first apply KCL and solve it. So now what are you going to do? You have a small signal model that looks like this. R pi, Gm V pi, R naught in parallel. All three are in parallel. So you will apply a test voltage here. I mean, it can be Vi. Here the test voltage is Vi. And we are finding the current II flowing through that. Now this current II splits into three currents. Now look at this. Vi, can I say Vi equals V pi? Because the Vi is node voltage at this point. This is an AC ground. So Vi equals V pi. Okay, Vi equals V pi. So I can say the sum of the currents. The current through this resistor is actually Vi by R pi plus Gm V pi or Vi. Vi equals V pi. So Gm Vi plus Vi by R naught. Now I am going to represent this Gm 1 by Gm as 1 by Gm. So this can be written as Vi by R pi plus Vi by 1 by Gm plus Vi by R naught. So now if you can see, this is nothing but if I take Vi common out, I have three resistors in parallel. 1 by Gm plus 1 by R naught. The three resistors are R pi, R naught and 1 by Gm. So it's the parallel equivalent of all the three resistors, R naught, R pi and 1 by Gm. That will be your equivalent resistance seen here. So this is your II. So what is your equivalent resistance? Equivalent resistance is Vi by II. That is the inverse of this term, which is the parallel equivalent of the three resistors. Is this okay with everyone? In fact, when you are performing the analysis itself, you can immediately see, the moment you see Gm V pi, the voltage across it is V pi. You can replace this Gm with a resistor of value 1 by Gm. See, you can do this only if the collector and base are short circuited. Then only you can replace the Gm with 1 by Gm. Otherwise, you cannot do that, you should not do that. Okay? So don't do that unless the base and collector are short. So what you are left with is this parallel equivalent of the three resistors. So that's what I've shown here. R equivalent is this. Okay, so that from the values you can calculate R naught. Once you calculate the quiescent current, you know all the three parameters. Find the parallel equivalent, and that will be your equivalent resistance value. Okay. So now here we have given you a slightly, see, in fact, I haven't spoken much about this circuit. The reason, see, understand guys, every problem we are solving in this tutorial, you will be encountering this device very often in your course, throughout the course. In fact, BJT will try to finish it by this week. No, it was not Y, it was given in the question. In the question, it was short circuited. We have short circuited in the question itself. It was short circuited there. We didn't short circuit it. Especially, it was already given in the question. The question itself, small signal, was short circuited. No? Yeah. Okay, so this is one part. The next thing is, this is a very commonly encountered structure. So this is called as a diode connected BJT. So this is what we call as a diode connected BJT. So you take a 3-terminal BJT device and then short collector and base together. Now it becomes a 2-terminal device. This 2-terminal device behaves like a diode. Okay, see, once I short PN junction, so base is a P-type, see, assume this is NPN semiconductor. So it will behave like a base emitter diode. So this is base and this is emitter. Base and collector are shorted, so that diode is gone. So you'll be left with base emitter diode this way. And for small signal, you can approximate this as a resistor for small signals. And the value of the resistance will be 1 by Gm parallel R pi parallel R naught. So that's what we did in this lecture. So this is why it's a very important structure. You will often encounter this in circuits. Okay, so that's why we I specifically had given this question. This was in 2017. At that time I was teaching MUE, I had said this question. Now the next circuit is something like this. So you have 4 BJTs, 2 PNP transistors and 2 NPN transistors connected in series. If the base and collector, how will the current flow? Okay. So now his question is, okay, now I am shorting base and emitter, base and collector. What will be the direction of flow of current? See, once you short circuit your base and emitter, base and collector together, the current which will be flowing here, see, base terminal also will take in some current. Okay, and see, imagine you want me to show from a device's point of view. How will the current flow? You want that from a devices, or how? I don't understand what you mean by that. See, if it's a 3-terminal device, I directly short it, then I can directly see that this is emitter current. From case here, I'll see base current will flow through the base and collector current. But as far as the external world is concerned, this will look like a single terminal which is carrying both collector and base currents. Does that make sense? What did I say? Or you can look at it from the device also. You have short circuited these two terminals. Once you short circuited these 2 terminals, what will happen? If you apply a forward bias voltage here, this is a forward bias voltage for the PN junction. This is your base emitter junction. If you apply this, it will flow like a conventional diode. So that such a diode, because your base width is very small, it's called as narrow bias diode. Is that clear? So maybe I can explain that after the class to you. I don't want to interrupt a big class for that. Okay, after the class I'll explain if you have doubt. Yeah. Okay, so now you are given 4 transistors like this, and it's given to you beta is infinity for all the devices, and for all the devices assume reverse saturation current is 10 power minus 16 amperes. Okay, so the expression for if whenever you short circuit, I just told you guys, if you short circuit a BJT, that becomes a diode. This can be approximated as a simple diode structure. So now can you guys quickly see that this is PNP transistor. So if let's say I take a PNP transistor like this and short these 2 terminals, this is P, this is NP, but N and P are shorted. So I will just treat this as one forward bias diode. So can I say, if I'll replace the transistors by 2 diodes like this. First one diode, the upper transistor. Second transistor is a diode. Third is a diode. Fourth is a diode. And all 4 are shorted. And I'm asking you to find what is the node voltage Vx given in the circuit. So no current is flowing through this. This is also 0. So you don't have to worry about this circuit as of now. I'll ignore the circuit. So because no current is flowing there, now I'm supposed to find this node voltage Vx. This is given to be 1.6 volts. Now tell me, you have 4 diodes in series. All diodes are carrying same current. Yes, you are right. So all diodes are carrying same currents. If all diodes are carrying same currents, what is the VBE for all the diodes? Can I say all diodes have same VBE? The VBE equivalent is same for all diodes. 4 diodes have the same VBE equivalent. So I can write 4 into VBE equivalent or V diode will be equal to 1.6 volts. So the individual diode voltage is 0.4 volts. So now the voltage Vx will be 0.4 plus 0.4, this will be 0.8 volts. That's it. Vx is 0.8 volts. Now in the question, you are supposed to find, yeah, is that okay? Vx is 0.8 volts. I just expressed V8, which is 0.8 volts. That's it. Your answer is that. Vx you found out. Once you find Vx, the next part of the question is you are supposed to find the collector current in this device. Assume the device to be in active region. You know the base emitter device voltage is 0.8 volts. This is your base emitter voltage. If you know the base emitter voltage and it's given beta is infinity, what will be the collector current? What will be your collector current? Yes, Vx equals VBE for the right transistor. Not diode, it's a transistor. Yes, Vx will be equal to VBE for the right transistor. Now the right transistor, the collector current will be equal to the emitter current because beta is infinity. Because beta is infinity is equal to, therefore this will be equal to Is e power VBE by VT. And VBE is simply Is e power Vx by Vt. That's it. Is is given to you. Vt you know at 300 Kelvin. So you can calculate the collector current. Vx you know, which is 0.8 volts. You can calculate it.
Excuse me, sir.
Yeah.
Sir, if beta is infinity, 1 by GL resistance will still be there, right?
Yeah, that will be there. No, that depends only on collector current. Yeah.
Yeah, so I didn't get how IC will be equal to IE.
Which is in this transistor. No, see, if beta is infinity, what is your IC? IC is alpha times IE. Alpha will be 1,
Oh,
no?
got it, sir, got it.
Yeah. Yeah, how did we get IB as 0? Because beta is infinity. If beta is infinity, for a finite collector current, IC, the quiescent beta current will be, if beta is infinity, this will become 0.
Sir, can you also explain the VX part once again?
Vx part, okay. So I told you guys this is fine, right? If you want to understand Vx, it's very simple. If you understood that I can represent a BJT once I short circuit collector and base, a PNP transistor can be represented as a diode like this. Similarly, if I short circuit the base and collector, NPN transistor can also be represented as, because look at this terminal, this is now base now because you have shorted base with collector. That's a P junction. And this will be NPN, right? So we have P and N are short circuits, so I can treat them as either P or either N. But if I treat it as P, I should treat it as P because it's connected to the base here. The positive voltage goes to the base. This I can represent it as a single diode, base emitter diode. So replace this transistor by a diode, replace this transistor by a diode, replace this transistor by a diode, and this one by a diode. Now you have 4 diodes in series. 4 diodes in series. Since they are all in series, they are all going to carry same current. Since they are all carrying same current, the voltage drop across the diode will also be same. I will call it VD. VD as the voltage diode. VD, 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 VD. So 4 VDs, they are all in series, should be equal to 1.6 volts. That's given to you in the question. VDD is 1.6. Okay, what about IB of the right diode? It's given beta is infinity, therefore IB is 0. If beta is infinity, on the right, there is no current flowing because beta is infinity. IB becomes 0. Right? The base current, right? The current going through this is the base current of this transistor. So that is 0. That's
Sir,
it. So you have.
sir, but if beta was not infinity, suppose it was some finite value, then we cannot use that like the voltage divider rule,
Yeah,
right?
obviously, yes, obviously, yeah.
Yeah, okay, sir,
See,
got it.
but we won't give you a question like that, right? That will be too much of calculations. No, we just want to test your understanding. So that you will have simulation software to do that, all those calculations. Exam and testing is really mainly for intuitions, how whether you understood the circuit or not. That's it. That's the way we go. Okay, so you got it. Vx will be 0.8 volts. That's it. Once you know Vx, you can calculate the collector current in this device. The Vx will be equal to the VBE. Is IC equal to IE equal to GM into 0.4? No, 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 no. That is for small signal analysis. This is DC analysis, right? So we may not be able to exactly say that. Yeah, that's a small signal analysis. IC and IE will be equal to, for the circuit, IC will be equal to IS. You have to use the large signal model and find out Vx by Vt. Yes, IS e power Vx is 0.8. 0.8 divided by Vt is 25 millivolts or 26 millivolts at 300 Kelvin. So you have to use that equation and find out the value of collector current. DC current, you have to use a small equation to compute it. Okay, so I think I've used an exact expression, but there is -1 also there. So you'll get 2.3 milliampere in the question. Okay, guys, the next two problems we'll solve it in the tomorrow's class. Okay, yeah, thank you. So if you had any doubts, you can stay back and ask. I'll stop recording now. Yeah, we're done.